Now, right now, we're using version 4 IP addressing. And version 4 is a 32-bit number. Now, there are only so many combinations of 32-bit numbers, and it turns out that right now, there are more devices that can connect to the internet than there are 32-bit numbers. So we have completely exhausted the IP version 4 range. So the world is moving on to IP version 6, which is a much larger addressing scheme. But in the entertainment industry, we're still using IP version 4, mostly because we primarily build private networks. We don't want to connect to the outside world. We don't want to connect to the internet unless we have to. And there are cases where you might have to, or want to. If you want to, for example, control the lighting on the Empire State Building, then chances are you're not going to go up to the penthouse suite of the Empire State Building and make a hard connection to the lighting system. Chances are you're going to want to sit in your office, connect to the system over the internet or some other means of connection. But there are lots of applications where you need to go out on the internet. But most of the time we're building private networks and we don't want anybody else into our network. So we will continue to use version 4 IP addressing for the time being. Now, the way IP version 4 works is it's a 32-bit number, but it's written in quad-dotted decimal notation, meaning quad is 4. There's 4 segments. They're separated by a dot, and these are decimal numbers that range from 0 up to 255. Now, one of those is going to be for the router or the switch. And then one of them, as you learned earlier today, is the broadcast address. 255 is the broadcast address. So that leaves 254 possible options for that number. There's 2 parts to an IP version 4 address. There's the network part and there's the host part. Now, any computer or device, console, light, whatever, on the network is referred to as a host. Which, that seems kind of backwards to me. I would have named him a guest, but, they didn't consult me, so I get no say in the matter. So anything on any device on the network is called a host. So in order for any 2 devices on the same network to be able to communicate with each other, the network portion of the IP address has to match, and the host portion has to be unique. Because remember, the host portion is kind of like the street address. If 2 houses on the same street have the same address, the mail carrier wouldn't know where to deliver the mail. So every host portion has to be different than anybody else's. Now, the length of the network portion and the host portion is variable. So you can have a very large network portion and a short host portion, or a short host portion and a short network portion and a large host portion. And the length of the network portion, and consequently the host portion, is determined by the subnet mask. Remember, when you were manually configuring your IP address, if you're on Windows, you saw a window like this. And you have 2 options. You can either obtain an IP address automatically using DHCP, or you can choose to manually configure your IP address by choosing use the following IP address, and you type it in. Right below the IP address is the subnet mask. And when the subnet mask is written in quad-dotted decimal notation, it makes no sense whatsoever. It's only when you convert it to binary numbers that it starts to make sense. So here's the IP address. Here's the binary equivalent of that decimal IP address. Here's the subnet mask. Here's the binary equivalent of the subnet mask. And you'll notice that when you convert the subnet mask to its binary equivalent, it becomes a string of 1s followed by a string of 0s. And wherever you see a 1, that corresponds to the network portion of the IP address. Wherever you see 0s, that corresponds to the host portion. So for example, if I have the IP address 192.168.5.10, if I convert it to its binary equivalent it would look like that. Then if I have the subnet mask 255.255.255.0, when I convert it to its binary equivalent, it looks like that. And everything that lines up with the ones is the network portion of the IP address, and everything that lines up with the zeros is the host portion. So in this case, the network portion is 192.168.5, and the host portion is .10. Now, with this subnet mask and this arrangement, this allows me up to 254 devices on that one network. If I want a bigger network, if I have more than 254 devices, so say for example, if I was working on the 2012 Olympics and I needed a network with 70,500 hosts, this would not work. What I would have to do is change the subnet mask. So instead of 255.255.255.0, it would have to be 255.0.0, because if it was 255.255.0.0, that would only give you, I think it's 65,000 possible hosts. So if I went to 255.0.0.0, that gives me 65 million, I think, hosts. So that would be big enough to accommodate almost any size network. So now typically what you'll find is that if you're using a 10 dot address, usually you'll have a subnet mask of 255.0.0.0. If you're using a 192.168 address, usually the subnet mask is 255.255.255.0. And if you're using, this is a bit more obscure, a 172 dot address, it's usually 255.255.0.0. So, and then, because the subnet mask is a 32-bit number, there are actually 31 different possible subnet masks. The only requirement is that it's a string of ones followed by a string of zeros. But these are the most common ones that you'll see. Now, when we're talking about IP version 4, there are what are called routable IP addresses. Those are IP addresses that are allowed to go out on the internet, that we can use out on the internet. And then there's another block of IP addresses that are reserved for private networks. And those are called non-routable IP addresses. And there's only a handful of non-routable IP addresses. And those are 192.168.something.something and 10.something.something.something, and the more obscure 172.16.0.0 through 172.31.255, and that's supposed to be .255 also. .172.31.255.255. Those are the only non-routable IP addresses. So again, what happens when you have a cable modem, you want to go out to the internet, you have your private network in your house, you probably have a Wi-Fi router, and so you send an email to the router, and when it crosses the firewall, it converts it from a non-routable IP address to a routable IP address that your internet service provider has leased to you. So that email can go out on the internet, and then when it comes back, it goes over the firewall and goes back to the private IP address again. Now, Zach brought up the point that these fixtures, and some fixtures are like this. And so here's what happened. If you go back and look at the history of ArtNet, when ArtNet first came out, they wanted you to use an IP address that starts with 2. They wanted you to use a 2 dot address. Well, if you notice, a 2 dot address is actually a routable IP address, even though we're using it on private networks. And I asked Wayne Howell about that once, and he told me the reason he did that is because there are some switches that will block non-routable traffic. So now you can go into the configuration and turn that off and allow non-routable IP addresses to get through the switch, but he wanted to make it simple. So rather than force you to go into your switch or router and configure it to allow non-routable IP addresses to pass through it, he thought it'd be easier just to use a routable IP address. The problem with that is that somebody owns that 2-dot address. So if it accidentally gets out on the internet, now you've just broken the internet. Well, not really, but it just won't work. So the second version of ArtNet, they switched over to a 10-dot address, which is a non-routable IP address. And that's why now some fixtures will only allow you to use a 2-dot or a 10-dot address when you're using ArtNet. But the truth is, ArtNet will work with any IP address. You can choose any IP address in the world, and ArtNet will work with it. But sometimes you're restricted by the fixture to a certain range of IP addresses, either a 2-dot or a 10-dot. So it would be much simpler if the fixtures ran DHCP and would allow any IP address. So that's probably why this particular fixture does not have DHCP, because they want you to use a 2-dot address or a 10-dot address. And I believe that whole approach is obsolete now, because any IP address will work with ArtNet. Okay. Now, there's also something called a loopback address. A loopback address is internal to your machine only. If you're running two pieces of software on the same machine, in order for them to communicate with each other, you use a loopback address, which is 127.0.0. something. So, for example, yesterday Daniel was running his which controller? Huh? No, the controller. Oh yeah, Jan's Vista. So he's got Jan's Vista on PC. He's also running a Vision visualizer, ESP Vision visualizer, which is actually now a Vectorworks Vision visualizer, because Vectorworks bought ESP Vision. But anyway, he's running the control software and the visualizer on the same laptop. So in the settings, he would go in and configure the IP address for a loopback address, which is 127.0.0. something. The same thing if you're running M-Series console and you want to run a visualizer on the same laptop, or a Grandma and Grandma 3D on the same laptop. And that was the mistake that I made when I was trying to do my pixel mapping. My IP address was actually set for a 127 dot address, so the data was being generated, but it wouldn't leave the computer until I changed the IP address, and then it went out the Ethernet port to the pixel driver. So that's why you would use a 127 dot address. Okay. Now, the rest of the world is on to IP version 6. They call it next generation addressing, so you know it was put together by some Trekkies. But it is a 128-bit address. Now, that's a lot of bits. That's a lot of bits. I read somewhere that with the IP version 6 address, there are enough combinations of 128-bit numbers that there is something like 10 million possible IP addresses for every square meter of the Earth's surface. So it's unlikely we will ever run out of IP version 6 addresses. Now, with IP version 6, there's a fixed network portion of 64 bits and a fixed 64 bits for the host portion, so it does away with subnet masks. Now, right now you have the ability, most switches have the ability to use an IP version 6 address. I could have configured our router to issue you an IP version 6 address, and your machine has the ability to use an IP version 6 address. Some of you may have noticed that if you look in the manual configuration, IP version 4 is at the top, version 6 is at the bottom. But most of the time, you and I are still going to be using IP version 4 addresses. There's no need to move on yet. I have seen some software that does use version 6 in our industry, but that's only because Apple is kind of forcing their hand. If you want to sell an app on the Apple Store, it has to accept an IP version 6 address. So it's coming. It's coming. Now, we said earlier that Ethernet is a protocol for connecting different kinds of devices on the same network. So it doesn't care whether you're running a Mac, whether you're running a PC, whether you're running a Chromebook. We can all get on the same network using Ethernet because it doesn't care. It's just a way of transporting data across the network. So it's like, we don't care what kind of passengers are loaded into the car. We have the roads to get them there. So it came out in 1983, and it was actually developed by 3 companies. Digital Equipment Corporation, Intel, and Xerox got together and created this protocol. Now, at that time, in 1983, there were lots of competing networking standards. When I started working at High-End Systems, we used Novell Network, which is a competing standard to Ethernet. But later on, this kind of Ethernet kind of became the de facto standard. Everybody kind of gravitated towards Ethernet. Everybody started using Ethernet. And then eventually the Institute of Electrical and Electronic Engineers took it over and formalized it and made it a computer industry standard protocol. Technically it's called IEEE 802.3. Now, there are different versions of Ethernet. The very first version that came out was 10 megabit per second protocol. And if you compare that with the speed of DMX, the baud rate for DMX is 250,000 bits per second. This is 40 times faster than DMX. The slowest Ethernet is 40 times faster than DMX. So that should tell you that you should be able to transport about 40 universes of DMX over the slowest Ethernet network. Later on, they came out with 100 megabit per second Ethernet. They called that fast Ethernet, which is kind of a joke now, because later on they came out with 1,000 megabit per second Ethernet. Now, 1,000 mega is a gigabit. So now we have gigabit Ethernet, and today we actually have 10 gigabit and 40 gigabit, and the last I read, they were working on 100 gigabit Ethernet. I just got an email from Red, and he sent me an article about how they had successfully deployed a 400 megabit Ethernet network and a 200 megabit Ethernet network. So my guess is that once all of those standards are completed, they'll probably move on to 1,000 gigabit Ethernet, which would be terabit. So I think terabit Ethernet is probably around the corner. And so isn't that wonderful? So now, earlier we set up our network and we did some commands in the terminal app. The ping command is one of them. So you should, if you successfully set up a network and it tests out properly, then when you ping an IP address, you should get a response that looks like this. It'll tell you that you got 64 byte reply from a particular IP address, and it'll tell you the amount of time it took in milliseconds. Actually, this is tenths of a millisecond. So this was a very fast ping. But anyway, it'll tell you the amount of time it took for the round trip for the ping command to go out and come back again. And you'll like we talked about earlier, you'll notice that every ping has a different round trip time. That's because it very much depends on the amount of traffic on the network in addition to the hardware you're using for the network. So if there's a lot of traffic, it's going to take a longer period of time to ping back. If there's not, then it'll take less time. And it'll tell you how many packets were transmitted, how many received, how much packet loss you had, and give you some other information. So in Windows, to run a ping command, you would hold the Windows button down, press R to open the window to type in CMD for command. In iOS, You do a spotlight search, you type in terminal app, and that will open up that DOS prompt. Now, a good question to ask yourself is, how many universes of DMX can you transport using an Ethernet-based protocol on different types of Ethernet networks? So the way networks are designated is they're called by the speed of the network and the type of transmission and the type of media. So 10 base T, for example, means 10 megabit per second Ethernet using baseband transmission. Now, baseband transmission just means that we're sending the data over without any carrier signal. Like when you transmit television or radio signals, there's a high-frequency carrier signal that helps carry that signal a long way. We don't use that with Ethernet networks. It's only the data that is transmitted. That's what's called baseband transmission. And then the T stands for twisted pair copper wire. If it was fiber, it would be FL for fiber link. So if we say 10 base T, what we mean is copper wire Ethernet cable with a 10 megabit per second network interface card and network. Now, in theory, so if this is 10 megabits per second, DMX is 250,000 bits per second. So if you just do the straight math, then that will give you 40 universes. So in theory, you should be able to transport 40 universes of DMX using a 10 base T network. Now in real life, there's latency in the network. If we have a lot of switches in the network, if there's various things that can slow down the throughput of a network. So if we have a throughput of 50%, that means in practice, we would have something like 20 universes of DMX that we can get through a 10 base T network. And the truth is, it's probably somewhere in between those two numbers. Now, when ARTNet came out in 1998, they originally allowed you to configure up to 40 universes of DMX. And later on, when they came out with 100 base TX, 100 base TX means 100 megabit per second, baseband transmission, using twisted pair copper wire in full duplex mode. That means two pairs of wires at the same time. And in theory, that would be 400 universes of DMX, but with the 50% throughput, it's 200. So it's, again, in real life, it's probably somewhere in between the two. When ARTNet 2 came out, then they allowed you to configure 255 universes of DMX because of now we have 100 base TX networks. Still later, when 1000 base T came out, this is a gigabit network, then in theory, that's 4,000 universes. In practice, it's more like 2,000. Now, when we started using gigabit networks, then ARTNet 3 came out, and by that time, they just said, I'm tired of playing this game. We'll just open it up, and we'll say you can configure up to 32,000 universes of DMX. Now, there is no hardware in the world right now that can actually carry 32,000 universes of DMX over an Ethernet network. But the software will allow you to configure it. So if you want to impress your friends, you can label one of your universes 32,000. Wouldn't they be impressed with that? So, and it's funny too because, oh, I'm sorry.
That's okay. I was just thinking out loud like this. The world's becoming wireless. We even have wireless power. The wireless radios are so inexpensive, so small. When's all the wire going to go away?
Yeah, good question. Ray said that wireless transmission is becoming less expensive, more reliable, and they're so small and they're becoming ubiquitous. So his question is, when is wired going to go away? My guess is probably not in our lifetime, because wireless, regardless of how cheap wireless DMX get, it's still cheaper to use a copper cable, I think. And
Not when you factor in the labor.
When you factor in the labor, yeah, well, I can see that in certain situations. In certain applications, that's true. but they're still firm believers that a wire is more reliable than wireless. So I think that for the time being, at least for the foreseeable future, the fallback will be, we'll always rely on wired, and the fallback will be wireless. Who knows? I thought when ACN came out, I thought DMX was going away. I was wrong, so I could be wrong about this too. But I think we'll continue to use wired networks for the foreseeable future.
Looking at it from an audio side, nobody thinks twice about running wireless microphones.
True, yeah.
99% of the shows and rigs out there are wireless in some way.
Yeah.
When it comes to audio. So it just makes sense that eventually
But
lighting
only
side
to
will
a
have to
point,
embrace it.
only as an access point. It's from the transmitter to the receiver, but when you go into the console, you don't have 32 channels of Bluetooth or 32 channels of receiver built into the
Not into the console, but
into
you've
the
got
console.
a stack
There's
that's
still that
foot
point
away.
of people want to eliminate the other possibilities, and so the ability to make a handshake between A and B with nothing in between, a laboratory lockdown on cable, is always going to be there, because to test it and to do other things in a virtual space, there's other factors that play into that.
Yeah, and here's the other thing to consider as well, Ray. There are environments that are really challenging to do wireless. You know, at the Super Bowl halftime, for example, they have a frequency coordinator because there's so much wireless. They assign this bandwidth and that bandwidth to make sure that nobody interferes with each other. They're completely tapped out. And that's why a certain supplier of wireless DMX was able to get their foot in the door, because they have a frequency-based system that's completely out of the 2.4 gigahertz range. They're down in the 900 megahertz range. The same thing with, down the street in Hollywood, there's a lot of wireless. When you go into a studio, they have a wireless monitoring so that the director can basically have a viewfinder through the camera live while they're shooting. He can see exactly what's going on a giant monitor, and so, or she. And so that is a very important wireless connection. But then you have wireless audio, and you have wireless lighting, and you have wireless lens focus, and all sorts of wireless. But they're very challenged to make it all work without interfering with each other. And it's almost to a crisis point now. So in certain environments, it is very challenging to get wireless to work. I'm a firm believer in wireless. I like wireless. I use it whenever I can. But I understand the need for, sometimes you need a solid connection. So, and who knows? That may change. But right now, it's still very much necessary.
But going back to your moving from the IP4 to the IP6, there's still, unless they create more frequencies, there's still a limited bandwidth, and those addresses are being used up by all the multiple devices. We're running out of individual
space, yeah.
And that congestion is not only causing problems, but at some point there's a theoretical limit.
There is a limit.
How many addresses can be.
Yeah.
So I understand that. There's always a theoretical limit to what we have now.
Right.
But necessity is the mother of invention.
Yeah.
Right? So what we have now, remember, digital television didn't exist 25 years ago, and now look where it's at. So
Yeah.
there's always going to be something better.
That's true. The technology could completely change tomorrow. So, okay.
Sorry.
No, this is quite all right. It's a fascinating discussion. All right. So anyway, these are the limits of the number of universes that you can carry using Ethernet or Ethernet-based protocols. A friend of mine emailed me the other day, and she's putting together several lighting systems for permanent installations across the country. So she's looking at different options. And she'd emailed me and asked the difference between ArtNet and streaming ACN. And I gave her some information, and she looked at it, and she did some more research, and she emailed me back a couple of days later, and she said, "Oh, I found something out." She said, ArtNet you can configure up to 32,000 universes of DMX. But with streaming ACN, you can use 64,000 universes. So therefore, streaming ACN must be better than ArtNet. And I said, well, yes and no. In theory, you can address up to 64,000 universes of DMX using streaming ACN, but there is no hardware in the world that can even get close to that. The limitations are about 4,000 in a perfect world, 4,000 universes. I don't care what the software says, there is no hardware in the world that can transport more than 4,000 universes unless you go to a 10 gigabit network. And they do make 10 gigabit switches, but those are primarily for multiple controllers sending streams of data. They also make 40 gigabit switches. So, but even if you had a 40 gigabit switch, that's 4 times as much as a gigabit switch. No, sorry, it's 40 times as much. So that would be 1,660,000 universes. I guess in that case, yeah, maybe you could. So, but anyway, the point is, you know, there are hardware limitations, there are software limitations. So let's talk about Ethernet-based protocols, okay? So ArtNet, right now, there are 4 versions of ArtNet. The first version came out in '98, and then we had ArtNet 2, ArtNet 3, and ArtNet 4 came out in December of 2017. But the whole idea behind ArtNet is that it allows you to send DMX over an Ethernet network. So it takes the DMX data that's generated by the console, it puts it in an Ethernet wrapper, and it sends it out over the network using a Cat5 or Cat6 cable. The receiver gets it, takes out the data, and now it's got the DMX data. The advantage is you can send multiple universes of DMX over a single Ethernet cable, whether it's Cat5 or Cat6. One of the advantages of ArtNet is that it does work with RDM. Streaming ACN does not. And most consoles today do have the ability to output multiple Ethernet-based protocols, including ArtNet. Now, when you configure ArtNet, you go into the settings on the console, and there will be a port address. A port address is a 15-bit number, so that gives you 32,768 possible port addresses. Now, most consoles break that into a subnet or a net and a universe. The combination of the two make up the port address. So typically, you'll have an 8-bit universe number that goes from 0 to 255, and a 7-bit net number or subnet number. So that goes from 0 to 128. The combination of the two gives you a 15-bit number that goes up to 32,000 or so. You can also configure the DMX universe. Most of the time, the universe is part of the port address, and then you have the net, or sometimes it's called the subnet. So there's different terms that mean the same thing. Now, remember, the broadcast domains have to do with how much data, where the data is being sent, and the byproduct is how much data is being generated and sent out over the network. So the whole idea is we want to create a network that is fast and responsive. So when ArtNet first came out, it was a broadcast network, and that was back in the day when we didn't have very sophisticated devices. We weren't doing a lot of pixel mapping, if any at all. No, we weren't doing any pixel mapping in '98. So we didn't generate a lot of traffic. So it was okay to broadcast everything across the network. That did not present any problems. Later on, when we started developing more sophisticated devices that generate more data, and our systems got bigger, then ArtNet switched over to unicast, and now when you go into a console to configure a console to output ArtNet, then usually the default is to broadcast. You have to uncheck the default, and if you stop broadcasting with ArtNet, then you're going to be unicasting. Now, if you're unicasting, that means the console has to know the IP address of every device on the network that it's sending to. And as far as I know, that is a manual entry. I've never seen a way to do it without physically typing in each and every IP address, which if you have a big system, that's a big chore. On the other hand, streaming ACN uses multicast. And multicast is where the fixture, when you first set up your network, you connect your fixtures to the network. Because the fixtures are running IGMP and the console is running IGMP, then the fixtures are going to subscribe to a multicast. So they will subscribe to a particular universe of DMX. And multicast makes the most efficient use of the bandwidth because it generates the smallest amount of traffic, less than unicast. So streaming ACN, or little s big ACN, is another protocol. This is an industry standard protocol that transports DMX data over an Ethernet network. And just like ArtNet, it puts the DMX data in an Ethernet wrapper and it sends it out over the network. And you can send multiple universes of DMX using a single Ethernet cable. But streaming ACN does not work with RDM, whereas ArtNet does. So a lot of consoles today, you can either configure it to output DMX, ArtNet, or streaming ACN, or some other proprietary protocol like ETCNet. When you're setting up your streaming ACN, typically you will have a priority setting. So a priority setting gives you some flexibility in how you set up your system. You may, for example, have a wall station and a console. So if you set the priority for the console higher than the wall station, that means as long as the console is sending data, it's going to take priority over everything else. So nobody can come and take over your show. On the other hand, when you shut off the console, then the priority falls back to the wall station. There are other uses for priority. You could, for example, set priority for house lights, or you can set priority for fog machines, that kind of thing. It also, some consoles like the Grandma, I'm not sure about the M series, but some consoles, when you configure it to output streaming ACN, give you a time to live, a TTL. You may have seen that when you pinged, that the TTL was also listed. So time to live is a way of preventing stray packets from bouncing around the network. And the way it works is there's a time to live counter, and every time the data hops from a router to router, it decrements the time to live. So that way, if a packet can't find a home and it keeps bouncing around the network, eventually it'll die and it'll get swept away and be removed, and it will prevent too much traffic from building up on the network. Now, we talked about how some layer 2 switches will convert multicast to broadcast traffic. So I've never encountered that myself, but I've heard that that can be an issue. And then also streaming ACN uses IGMP snooping. So snooping is where it's sending out commands going, hey, do you want to subscribe to a multicast? And if the receiving device is running IGMP, then it will say, yeah, I want to join this multicast or that multicast. So that in a nutshell is how streaming ACN works. Now, of course, streaming ACN does not do RDM. That's why right now they are developing RDMNet. RDMNet will then work with streaming ACN, and together that will allow you to use streaming ACN and RDM at the same time. Yeah, Ray?
So they're two separate protocols, but they'll work in...
Yes, they're two separate protocols that will work together much the way DMX and RDM does. Okay? Now, how do you troubleshoot Ethernet networks? It's challenging because with DMX, there are a lot of handheld tools that you can use to figure out if the console is outputting DMX. You can look at the timing signal, you can look at the data, but how do you do that with Ethernet-based protocols? Well, there are applications that you can run. You can download them, and they're all free, and you can use them to, these are what are called packet sniffing applications. The most common packet sniffing application is Wireshark, and it is used by IT professionals all over the world. So if you're in IT, then you know about Wireshark. You probably use it a lot, use it for troubleshooting. Now, there's a bit of a learning curve with Wireshark. It's not necessarily that easy to use. It takes a while to figure out how to use it. What I did when I was trying to learn Wireshark, what happened was I was over in Sweden, and I got a phone call from a friend who's having trouble with an Ethernet network. And he actually wanted me to come to Las Vegas to help them troubleshoot, but I was in Sweden, I couldn't do it. So we ended up emailing back and forth and talking on the phone and troubleshooting it. And that really opened my eyes to this problem. Wow, how do you troubleshoot ArtNet traffic? And I researched it. I found Wireshark. I already knew about Wireshark, but I downloaded it and I tried to use it, and it's kind of daunting. You know, you're looking at this big steep learning curve. How do you get up the learning curve? Well, I subscribed to there are online classes for IT professionals, and one of the offerings is there's a website called itpro.com. So itpro.com teaches classes on every aspect of computers, programming and HTML, including Wireshark. So you can subscribe, you can buy an annual subscription, or you can buy a monthly subscription. And if I remember correctly, I think it costs $15 to subscribe for 1 month. So I signed up, and I binge watched Wireshark videos. I know, while you guys are binge watching King of Thrones, I'm so nerdy. I'm binge watching Wireshark. And so I learned how to use Wireshark. I'm not an expert. I'm not, the most knowledgeable about, how Wireshark works, but I learned enough to get by, and now I can, in most instances, I can fire up my laptop, tap into the network, and figure out how, is the console outputting Ethernet-based protocol data, and you can see it. Now, there's some tricks you have to know. There's some tricks, So, for example, if the console is broadcasting data, it's a real simple thing. You tap into the network, and regardless of your IP address, if you're on the same network, if you can ping the console, you should be able to see the traffic. On the other hand, if you're unicasting, if the console is unicasting, it's not going to send data to your laptop. So what do? Well, one thing you can do is you can take a switch like this, and this is exactly why I carry the switch with me. This switch does port mirroring. So if I were to plug the console into the switch and then plug that light into the switch, you can go into the configuration, the browser page for the switch, and configure this port to mirror the data on that port. So any data that goes out of this port is mirrored on the third port. So if I plug my computer into a mirrored port, regardless of my IP address, I can see unicast data. Same with multicast. So things like that allow you to sniff the traffic and start troubleshooting. So if you can identify, and usually the data will say the IP address that it came from, where it's supposed to be going to, and what type of data it is. So, in the header, it'll tell you, it'll say ArtPol or whatever kind of traffic it is. So now DMX Workshop is another packet sniffer, and this is written by the folks at Artistic License, the same people that invented ArtNet. So this is a great ArtNet troubleshooting tool. It's a bit easier to use than Wireshark. There's still a little bit of a learning curve to it. The hardest part I found is to identify which network interface card you need to be looking at to sniff the data. Because what you'll find is when you connect to the network and you look in the list of network interface cards, there's a whole bunch of them. And you can do it by trial and error, but that sometimes you're chasing your tail and it's hard to do. So it helps to have those commands like ipconfig and ifconfig, because that will list all of your interfaces, and you can identify which one you need to use to sniff the traffic using DMX Workshop. So that's a good, powerful tool to use. And there's some other tools inside of that application. So you should be able to see the DMX data, the values of the DMX, as well as look at what's inside of the Ethernet packets. And then ArtNet Omnitor is another free packet sniffing application. And it's, as the name implies, it works with ArtNet. And then Streaming ACN Viewer, or SACN Viewer, is a packet sniffer specifically for streaming ACN. So it does much the same thing that ArtNet Omnitor does, except the name's not quite as cool. But, same idea. These are both very simple to use. Very simple to use. Okay? And then I already talked about port monitoring and port mirroring, which is, important when you're trying to sniff traffic. Okay? So, now what I want to do is we have 2 hours left. We're going to take a 10-minute break. When we come back, what I'd like for you to do is I want you to download. So you're going to have to connect to the internet, download one of these applications, or all of them if you want, and we're going to hook up the console to the Wi-Fi, and let's see if we can figure out how to sniff some of the traffic coming out of there. So I guess Sean went home. Is Sean not feeling well?
He wasn't feeling well.
Okay. Is there somebody else who can configure the console to output ArtNet? Okay. Okay, there we go. So, but right now, let's go ahead and take a 10-minute break. Okay?